Good afternoon, class. We are looking at chapter 3, derivatives. Here's section 3.8, differentials and linear approximation. We are going to look at more examples. The radius of a blood vessel is 1.4 millimeters. A drug causes the radius to change to 1.3 millimeters. Use differentials to find the approximate change in the area of a cross-section of the vessel. So it's a circular shape. That's the area of a cross-section with the radius originally being 1.4 millimeters. Using the drug changes the radius. It shrinks it and it takes it to 1.3 millimeters. So originally, this is the radius. This is the radius. Now the new radius is smaller. And this is the difference between the new and old radius. Therefore, R, so what is the given? R is 1.4. dr or delta R is the difference between the two, which is always the new one minus the old one, which results in negative 0.1 millimeters. We should know the area of a circle is pi r squared. And since they want us to use differential to approximate the change in the area, that means we want dA and we are, so this is dr, everybody, the change in R. And we are approximating the shaded region. So given R is equal to 1.4, dr or delta R is 1.3 minus 1.4 or negative 0.1 millimeters. We should know the area is pi r squared. And we are interested in finding dA, in other words, approximating the shaded region. So since we do know that f prime of x is dy dx, then a prime of r must be dA dr, and we are finding dA. We know dy is the product of these two, and dA will be a prime of r dr. So we are going to use a equals pi r squared to differentiate first to find a prime of r or dA dr first, where pi is just a coefficient or a multiplier. Then r squared will result in 2r. Therefore, dA dr is 2 pi r. What is dA? The same thing times dr, or 2 pi r dr. We use the given to replace the r with 1.4 millimeters and dr with negative 0.1 millimeters. The product will result in negative 0.28 pi millimeters squared. We should keep it as pi in our calculation and show the work. An approximation using a calculator gives us negative 0.8796 millimeters squared, and you give it back with however number of decimals. So that would be the approximation of the shaded region. The exact change is delta A. How would you find the shaded region? This is going back to algebra, everybody. How do we find delta A, the change? Never mind calculus. The change in the area. Delta A represents the exact change in the area, like delta 1. We want the shaded region. So we find the area with the new r, meaning pi r squared, plug in 1.3. Then we find the old area with the radius of 1.4 pi r squared using r equals 1.4. Their difference would be the answer we are looking for as an exact answer. Notice the answer is negative 0.27 pi. Negative means it has gone down, it shrinks, because we are dealing with the blood vessel and the drug causing it to get smaller. And when you compare negative 0.27 pi millimeters squared to negative 0.28 pi millimeters squared, they're pretty close. A bacterial colony has population P of t equals 20t over 10 plus t squared in millions. T hours after a nutrient is introduced, use differentials to approximate the change from t equals 2 to t equals 2.4 hours. So what is given? T. dt or delta t is the difference between the two. 2.4 minus 2 is 0.4 hours. And we want to approximate the approximate change in the population. We want dp. How do we find that? Here's P of t, everybody. And P prime of t or dp dt, that means differentiate. And then as dy is f prime of x times dx, dp is p prime of t times dt. So we're going to call this f over g because we need to use the quotient rule. So p prime of t or dp dt uses the quotient rule, f prime g minus g prime f over g squared. The numerator is 20t. Differentiation with respect to t gives us 20 times the denominator, which is g 10 plus t squared, minus g prime, the derivative gives us 2t, times f, the numerator is 20t, and finally g squared, just write the denominator in the parentheses and square it. Let's distribute 200 plus 20t squared minus 40t squared, and we can combine these two. And by the way, the bottom 10 plus t squared quantity squared, I think I mentioned that. So over the denominator is squared. I'll simplify the numerator, and this is what you get. That's p prime of t. What is dp? Same thing times dt. We are going to evaluate this expression by using t equals 2 and dt equals 0.4. 2 squared, 4 times 20 is 80, 200 and minus 80, it's 120. This is 14 squared, you get 196, and 120 over 196 times 0.4, putting it into a calculator, results in 0.245 millions, which means 245,000 bacteria. The exact amount in the population change, simply put, using elementary algebra, plug in t equals 2.4, come up with the population at t equals 2.4, then plug in 2, come up with the population at t equals 2. Their difference is the answer, and that is 0.189 or 1 million or 189,000. And by any chance, if anybody says there is a discrepancy, and there should be, but is there a huge discrepancy? It depends on the ratio. If dt is very small compared to t, we get a better approximation. Use differentials to approximate 51 squared. And by the way, you may remember that in elementary algebra, they probably have discussed, because you know that a plus b squared is a squared plus 2ab plus b squared. So something like that can be done easily by memory. 50 squared plus 2 times 50 times 1 plus 1 squared is 2,601. So you can calculate this in your head easily, but we want to use calculus. I hope you remember that. So the very first thing is, when you want to do that, you need a function And what function? Just read the question. 51 squared, whatever operation you need. We need the squaring operation, so it must be x squared. The second step is to choose a number x close to 51 for which squaring is easy to compute. The closest number you can think of to 51 that you can easily calculate its square. What number comes to mind?
49.
So you can calculate 49 squared easily.
Can you repeat the question? Sorry.
The question is asking, choose a number x close to 51 for which squaring is easy to compute. The closest number, I just did that. It would be 50, because 50 squared, you should know, is 2,500. And so you have the function y or f of x equals x squared, and you have the number. What is delta x or dx? We are going from 50 to 51, the difference of positive 1. Delta x or dx is 51 minus 50. And again, just to make sure we understand why it's positive 1, we are going to use 50 to get to 51. If the question was, what is 48 squared, I hope you recognize dx as minus 2. Okay, because from 50, we want to go to 48. In any event, so we need to find f prime of x and dy, because f of x plus delta x is f of x plus dy. That's an approximation we're going to use. Okay, so delta y, we're going to use dy. And so with that being the case, we know f of x is x squared, but what is dy? First, let's differentiate, and we get f prime of x or dy dx equals 2x. And dy becomes the same thing times dx. Therefore, f of x plus delta x can be approximated by f of x, which is x squared, plus dy, which is 2x dx. And now we are ready to find 51 squared, which means f of 51, or f of 50 plus 1, which means into this formula, you replace the x with 50, dx with 1, Obviously, this is 2,500, this is 100, they add up to 2,600. And as I mentioned, the precise answer was 2,601. As you can see, they're extremely close. And the reason is because delta x or dx is fairly small in a matter of comparing to the choice of x. So 1 is much smaller than 50. Therefore, this approximation works fine. We can use linearization, and I don't want to go through the whole process. I just want to show you that linearization refers to finding a tangent line, and to find a tangent line and finally call it L of x. That's all. See? Just go with the point slope. So in order for you to find the tangent line, the question is for what? For f of x equals x squared. At what point? At x equals 50. So if x is 50 and you plug in, you get the pair 50 comma 2,500. What about the slope? Remember, f prime doesn't represent a slope. It represents infinitely many different slopes, and it becomes a slope as long as you fix the x. So at x equals 50. So the pair is a 50 and 50 squared or 2,500, and the slope is 2 times x, 2 times 50, 100. Now we are going to use the point slope y minus 2,500 equals m, which is 100, x minus 50. And if you simplify that, you get y, which we are going to call it L of x, is 100x minus 2,500. What were we looking for? 51 squared. Therefore, L of 51, 100 times 51 minus 2,500, and we must get a number identical to what we found here. In other words, differentials and linearization, they result in the same answer, and they must. So the answers must be, so those are equivalent processes, finding the differential and linearization, equivalent processes. That's why they have identical answers. To better understand this question, we are going to look at a similar question. We want to use differentials to approximate the square root of 27. So we need a function. What function do you think we need, class? Anybody? Look at the operation that you're doing. You're taking the square root of 27. So the function must be square root of x. Choose a number x close to 27 for which the square root is easy to compute. What is the closest number to 27 you can think of that you can take a square root easily?
25.
Beautiful. 25. Because we know square root of 25 is 5. And now from 25, we're going to go to number 27. Therefore, delta x is 27 minus 25, which is 2. So from where we are to where we want to end up. Again, to make sure we understand why this is positive 2, because you know square root of 25 is 5, square root of 27 with the positive delta x, whatever it is larger than 5. On the other hand, if we are interested in finding the square root of 24, we should recognize dx as -1, because from 25 we want to go down to 24, and we know the square root of 25 is 5. What is square root of 24? We don't know it, but this indicates it must be less than that. So with that being the case, we need to find f of x plus delta x, which is f of x plus dy. We have f of x, dy is missing, and dy is f prime of x dx, so we need to find f prime of x. To find f prime of x, we're going to change this to x to the power of 1/2. We've differentiated this many times. So we have f prime is 1/2 x to the power of 1/2 minus 1 makes it negative 1/2 or 1 over 2 square root of x. So that's f prime. We are interested in dy. So it's the same thing times dx. And now we are going to write f of x is square root of x. dy is 1 over 2 square root of x dx. We are going to find square root of 27, which means we want f of 27 or f of 25 plus 2. So into this, we replace the x with 25 and dx with 2 to evaluate. Square root of 25 is 5. So this is 5, this is 5, these 2 cancels out these 2. And we get 5 and 1/5 or 5.2. Now, if we use a calculator and with a lot of decimals, square root of 27 becomes 5.196152423, and it continues indefinitely because square root of 27 is an irrational number. However, with respect to the first decimal, they are identical, so it's pretty close. Here's the linearization. In order for you to use the linearization, you need to know that you have to find the tangent line. For which function? F of x equals square root of x. At what point? At your choice of x, which is 25. What would be the pair x comma y? Anyone? Plug in 25, square root of 25 or 5. What would be the slope? Over here. When you plug in 25, this becomes 5, 1 over 2 times 5 or 1 over 10. So you want L of x when the pair is 25 comma 5 and the slope is 1 over 10. So y minus y1, y minus 5 equals m 1 over 10 x minus 25. And 1 over 10 times x minus 25 over 10. And you move that and you combine them and you get 1/10 of x plus 5 halves. I'm assuming you can go from here to here. Now, if I plug in 27, I should get 5.2. I'm going to leave it for you to verify that. Make sure you verify that, everybody. As expected, they must be identical, and they are. They must be identical, and they are, because differentials and linear approximations, meaning finding the tangent line, are equivalent processes. Measurement error in a manufacturing process, ball bearing must be made with a radius of 0.6 millimeters with a maximum error of plus minus 0.015 millimeters. Use differentials to estimate the maximum error in the volume of the ball bearing. So as you can see in between, those are ball bearings. They are in the shape of a sphere, and we should know the area versus the radius, the volume versus the radius has the formula V equals 4/3 pi r cubed, as we've seen it before. What it says is that the radius is supposed to be 0.6. However, if it's smaller by this much, meaning if you subtract this from this and you get 0.585 millimeters, you get a smaller ball bearing. It still works, but if it's smaller than that, it will fall off, it will not. If it's larger by this much, plus 0.015, makes the radius 0.615 millimeters and makes the sphere larger and still works, no problem. But if it's larger than that, then it won't work, probably it gets stuck. So the given is that R is 0.6, dr or delta R is this number is plus minus 0.015 millimeters. And we should know the volume has the formula for this power cube. What are we looking for? Estimate the maximum error in what? In the volume, dV. Therefore, given R equals 0.6 millimeters, delta R or dr is given as plus minus 0.015 millimeters. And we should know this formula from geometry. The volume has the formula for this power cubed. Find dV. So, which means we have to find dV dr first, and then we multiply it by dr. So that means differentiate first. To differentiate this with respect to r, we keep the 4/3 pi as the multiplier, and all we have to do deal with r cubed, which is 3r squared, and the answer is 4 pi r squared. Now this is a v prime of r or dv dr, therefore dv is the product of these two. dv is 4 pi r squared dr. And if we plug in r as 0.6 or better yet 0.6 millimeters, dr plus minus 0.015 millimeters, put it into a calculator. It gives us an approximation with the pi, okay, of plus minus 0.0216 pi. You always want to keep the exact answer with pi. Now, if you put it into a calculator with a lot of decimals, you get plus minus 0.0678584 cubic millimeters. The units for dV is the same as the volume because it's the change in volume. So that's how you come up with the answer. Now the question is, what would be the exact difference in the volume? So in other words, if you ignore this part and find just the maximum error, never mind the differential, never mind the estimation, you find the volume when it's 0.6, the original volume, the correct answer. And then you add 0.015, you find the volume again. You subtract 0.015, you find the volume. Their difference is the actual error. In other words, for the upper limit, 0.615, we've added 0.015, the plus sign, cube it minus 0.6 cube. For the bottom one, 0.6 minus 0.015 gives us 0.585 cube it times 0.6. By the way, notice I have factored out the 4/3 pi. I haven't finished the calculation, but I wanted to show you. Here's the exact answer. We found the approximation here.